Yes, it is maths time again, and we're on the last bit of the moments chapter. So last little tilting bit, and then we're done. So what is tilting again? Well, tilting, as described in the previous video, is where a rigid body is on the point of tilting about a pivot, and that means that the reaction force normally at the other support is equal to 0. Now, in the previous one, what we did is we looked at where you've got solid supports like that, and there's tilting about those solid supports. This time though, we're looking at a beam that's maybe suspended by a couple of wires, and you can still get tilting in this situation as well. So we've got to think about this. Now, what have we got here? Tilting can occur where a rigid body is suspended. If a rod is held horizontally by 2 wires or cables, as shown below, so here's one wire and here's another wire, and it's about to tilt around D, then the tension in the cable at C is equal to 0. So what does this even mean? Well, let's think about this. If you took some heavy object and plonked it over here, right on the end, then what we've got to do is think about what's going to happen. Well, because this is very heavy, it's going to get the rod to tilt downwards on this end. But then what we need to figure out is what's happening over here. At the moment, this rope is nice and tense. But then, if this starts to tilt downwards and this comes upwards, this rope is now going to go slack. And if it is slack, then what it means is now the tension at C is equal to 0, okay? So that's what you got to remember. Make sure you note that down. It's super important, right? So copy anything you want down from there real quickly. And then what we'll do is we'll look at the situation the other way around. So this time, if we put a really heavy object on this side, and that's going to come downwards, then what does it mean? It means this end of the rod is going to go upwards. And so the string attached at D is going to go slack. And if it's slack there, there's no tension anymore. So that means this is now equal to 0. Okay, so super important. You must remember that. Now let's see how we can actually apply it. So we've got a non-uniform rod, AB, has a length of 6y. Okay, so we'll fill that in. 6y is from here all the way to the end. And it's got a mass of m kgs. It hangs horizontally in equilibrium from 2 cables. That's supposed to be 2, but that's fine. At C and D, where A to C is y and B to D is 1.5y, because that's all labeled already, as shown in the diagram. The center of mass of the rod is at the point T. Okay, so here. Perfect. So that's the center of mass. And we were told the mass was m. So we're going to put mg coming downwards there. What else have we got? A particle of mass 0.25 m is placed at B. Okay, so we're going to draw a particle in at B as well. So here. And that's coming downwards with 0.25 m, and we'll need to add g on the end, right? Because they gave us a mass, turn it into a weight, add g on the end of it. And that's placed on the rod at B. Okay. And the rod is on the point of tilting about D. Okay, cool. So remember, if it's tilting about D, what does it mean about the tension in C? It means that that is equal to 0. So now that we've said that, let's add our tensions in. Tensions at C, tensions at D. That's what we've got over there. And now what we need to show is that the distance A to T is 4.125y. Okay, so A to T, okay, that's that distance there from A all the way to T. So that one there is what we got to show. Okay, how are we doing this? Well, I think what we should do is this. Let's take moments about somewhere, or envision taking moments about somewhere. And if it's about to tilt around D, then you know what? I'm going to say we should take moments around D. So right over there. Now, do we know this distance in here? No, we've got no idea what it is. So for now, I'm just going to call it X. Do we know the distance here? Yes, we do. We've got 1.5y. Okay, perfect. So if I'm taking moments around this point, remember, because this is 0, we don't need to include it. And because we're taking moments around TD, we don't need to include this tension over here, obviously. So all we've got to do is clockwise equals anti-clockwise around this point D. So clockwise equals, I'm going to put anti-clock. And we're taking moments around D, so I'll just write that there. Now clockwise is going to be 1.5y times by 0.25 mgs. That's what we've got on that side. And for the anti-clockwise direction, we're going to have x multiplied by mg, so times by mg. Now we need to do some simplifying. Let's simplify the stuff down a little bit. So mg and mg can cancel from both sides. So we're going to get x is equal to 1.5y times by 0.25. So let's enter that in here real quickly. 1.5 times 0.25, that comes out as 0.375y. So that's what we've got. Now we know that this distance in yellow then, that I marked over there, is 0.375y. Okay. Now, do we have any information about this distance, C to D or something? What were we told? We were told the entire length is 6y. Okay, right. So the whole thing is 6y. So there, and that is 6y. And look what we've got. We've got y here and 1.5y. So altogether, that's 2.5y on either side. Which means then that in the middle here it must be 3.5y. Perfect. And now all we need to do to find the distance from A to D, was it A to T, is we just need to work out this distance here. So we can do that by doing 3.5y take away 0.375. So that distance in here is going to be 3.5 take away 0.375. And that ends up with 3.125y. And now to get the distance A to T, just add on y. So just add on 1. And there we go. So if we add that on, we've got 4.125y. And that's that. So a bit long-winded, a bit fiddly there, but if you've got a nice clear diagram, you should be able to solve it just fine. So there it is. And now it's time for you to have a go at this practice question. Quite similar to what we looked at before in previous videos, actually. So shouldn't be too difficult. Have a go, and we'll catch up in a couple of seconds. Okay, let's sort this out then. So we've got uniform beam, BD, so this is B, that's D. It's got a mass of 60 kilograms and a length of 8 meters. It's resting horizontally on two supports at C and D, so C is here. We'll call that RC, we'll call this RD. And it says BC is 3 meters, so from here to here is 3 meters. And if the whole length is 8, it means from here to here must be 5 meters. So you've got that. And we've got a boy of mass 50 kgs, stands at D, okay, so he's standing here to begin with, and walks along the beam towards B. Okay, so he's walking that way, he's walking that way, he's walking that way. And what we've got to do is find the distance the boy can walk past C before the beam begins to tilt. Okay, so here's what I'm thinking. I'm thinking the boy needs to be around here somewhere before this starts to tilt, right? Because if he gets to about here and he's reasonably heavy, this part's going to start to lift up, right? Because it's going to start to tilt downwards on this end. So what have we got? He's got a mass of 50 kilograms, so we need to put 50g going downwards here. And we don't know this distance, so we're going to call it x for now. And what else? What else? Well, we need to put the mass of the beam in as well, right? So the mass of the beam, 60 kilograms, and it was uniform, wasn't it? So that's going to be at 4 meters. So therefore, we can put that maybe over here, 60 over there. And because that's going to be 4 meters, that means that this bit was actually just 1 meter. So nice and simple, actually. And now all we've got to do is decide where to take moments about. I think if we stick to what we were thinking about before, if we take moments about here, because RD is going to be 0, so RD is going to be 0, we don't need to include RD. And then because we're taking moments about C, we can exclude RC. So we don't need that. Perfect. So all we've got to do is go clockwise is equal to anti-clockwise. And clockwise is going to be 60g times by 1 meter. Anti-clockwise will be 50g times by x. So we've got 60g is equal to 50gx. Get rid of those, get rid of those, get rid of those, get rid of those. So we've got 6/5 is equal to x, which can be also put as 1.2 meters. So what have we just found? Well, we found out that this distance here that he can stand at is 1.2 meters. And when he does, it's then on the verge of tilting, right? Because for this whole scenario, we set it up so that RD was equal to 0. So if he's standing at 1.2 meters away from C, it's about to tilt. So if he walks past this, well, goodbye, because he's gonna obviously tilt, and that whole beam is gonna topple over, and that will be it. So for the second part, identify the region where the boy cannot stand without making the beam tilt. Well, he can't stand anywhere further than 1.2 meters from C. Okay, so that's it. I hope that makes sense. And if that does, that's wonderful. If not, go back through it, watch it again. Okay, well done. I hope that's moments all cleared up, and we can move on to the next chapter, which is, I think, resolving forces. So until then, if you've enjoyed what you've seen and what you've learned, give me a thumbs up and subscribe, and hopefully I'll see you again soon in the next video.